Video, we're going to continue looking at voltaic cells and take it a little bit further. So we had looked at how to kind of create a diagram that looks like this for voltaic cells. See that first video if you didn't get a chance to do that yet. And you'll notice that we had said, hey, on your wire you might have a switch, you might have a voltmeter, which can display the voltage for this particular voltaic or electrochemical cell. And now the next question becomes, how do you know what this voltage is going to be? Can you predict this voltage from your starting materials? Can you even use this as a way to even figure out what's oxidized and what's reduced? So that's what we're going to take a look at today. So in your voltaic cell, it's always using a redox reaction. So again, something gets oxidized, something gets reduced. Whatever is reduced is essentially pulling the electrons toward it because it's gaining the electrons and it's pulling the electrons toward it through the wire. And whatever is oxidized is pushing the electrons as it loses them. So you have this kind of push-pull driving force, which we call the cell potential, or for short, for symbol-wise, we do E of the cell. This sometimes is also called the electromotive force or EMF. The unit for this is volt, so this is essentially voltage. Each anode, cathode, they have this potential to push or pull electrons, and we're going to look at the difference between them. And so the unit is going to be voltage, notice, and this is on your AP Chemistry formula sheet. It is a unit of work, joules, per charge, coulomb. And this is typically measured with a voltmeter or a potentiometer in your cell. If you're actually doing this in the lab, you can use either of these things to measure your voltage as well. So the AP used to have this whole separate formula sheet with these different half reactions. For now, on the AP, this would be embedded in a problem for whatever you need. But what you'll notice is these are a whole bunch of reduction half reactions, and they have a list of the potential in voltage on the left-hand side. And if we go down here, we see 0 defined. So basically, to generate this chart, what they did is they took this hydrogen half cell, they took this half reaction for hydrogen, and they made this one of the half cells in a voltaic cell each time, and they compared all of these different other reactions to this hydrogen half cell to see what would happen, what would be the voltage recorded if we use this hydrogen half reaction as our other cell every single time. So we call this the standard hydrogen electrode. This is the reference all other oxidations are compared to. They use this hydrogen, they try to use this as the reduction half cell each time. And if you see this little degree looking sign, just remember this indicates standard state, which is typically like room temperature kind of conditions, 25 degrees Celsius, 1 atmosphere, 1 molar solution, so that we can make sure we're using the same conditions each time and we're not varying anything about temperature, pressure, or concentration. But when we did this, we set, for each time we're doing this, we're setting that the potential of this hydrogen half cell to 0, and we're going to record the voltage produced each time something else is connected to this as the other half cell. And that's how they generated this particular table. And notice, since there's just a nice thing to notice, since there's no metals in this actual reaction, no solid, that's why they're using a platinum electrode. You still want something that conducts electricity well, something unreactive that's not going to take place in the reaction instead. Maybe it's graphite instead. You could use something like that too. And notice that you're seeing bubbling happen as this reaction goes because it's turning into a gas. Really interesting. Okay, so now let's talk about now we know how this this chart was generated. Let's talk about how to use this. So a couple of things to notice. Notice these are all reduction half reactions. So basically what happened was when each of these were used as the other half cell, reduction of these things occurred when hydrogen was used as the other half cell. And this is basically a measure of how much more likely these things are to be reduced than the hydrogen. So you'll notice that fluorine here is very likely to be reduced into F-. And anything below the hydrogen was a lot less likely to be reduced than the hydrogen, and actually those things ended up being oxidized when used against the hydrogen half cell. Now, even if we're not comparing these things to hydrogen, we can now start comparing these things to each other. Anything at the top of the list, since these are all reduction half reactions and these have high potential, all of these things are more likely to be reduced. All of these things at the bottom are more likely to undergo oxidation instead. So now, going forward, we'll take a look at this, is if you are given options for what could be an anode or cathode, the thing at the top of this list would be more likely to be a cathode, or happening at the cathode would be reduced, and the thing at the bottom would be more likely to be an anode, and we'll talk about that momentarily. Okay, so again, notice that these are all reduction half reactions. The electron in each case is written on the left side, so these are electrons that are gained. And even if I'm looking at the oxidation numbers, this is going 0 to -1, they're all going down, which makes sense if you're reduced. So if these all above hydrogen actually got reduced, these reactions would be going forward. If these below the hydrogen were actually oxidized, then we're going to start seeing that these should actually be going in the reverse reaction. So the thing oxidized would really be the thing on the right-hand side, and they would be going in reverse so that these electrons are loosed. So let's start talking about this. Let's do an example so we can actually see how to use this chart and how to take these half reactions off of this chart. So let's say you need to make a voltaic or a galvanic cell. Those are synonyms of each other. And all I'm telling you is I'm giving you that chart, and I'm telling you I want to make a voltaic cell out of nickel and aluminum. That's what I want as my materials. And I want to try to answer all these questions about it, figure out what's oxidized, reduced, what's the anode, what's the cathode, drawing a cell. Okay, so what we can do is if I don't have a full reaction, I can still figure out what's oxidized and reduced by using that chart, which is a chart of what we call reduction potentials, how likely it is to be reduced. So if I go over here and I find the two reactions, we're starting with aluminum and nickel. So let's find reactions that have aluminum and nickel. Oh, here's nickel, here's aluminum. And notice they're both on the right, the solids. That's totally fine right now. So these are the two possible half reactions that could be going on in my, as reduction half reactions that could be going on in my half cells. Which one of these is more likely to be the reduction that takes place? So remember, the cathode's the side of reduction. These are reduction half reactions and their potential. The higher the potential, the more likely it is to be reduced. So whichever one has the higher potential is going to be the reduction half reaction that actually takes place, and that would take place at the cathode. And I would leave that half reaction alone because, as you see, these are reduction half reactions. The electrons are on the left. So nickel is more likely to be reduced because it has the higher reduction potential. So that must mean that the aluminum would then be oxidized, and that would be happening at the anode. Now, if this is the reduction half reaction, as you see electrons are gained, what are we going to have to do to the oxidation half reaction when we write it as the reaction that's actually taking place in that half cell? We would have to flip it. Why? Because we want electrons to be lost, so they'd have to be on the right-hand side rather than the left-hand side. So just to sum this up, the more positive the reduction potential, and again, notice here we're comparing two negative numbers. That's fine. You're just picking the one that is higher or more positive. So whichever is the higher reduction potential, the more easily an electron is gained, the more easily it is reduced. And this is kind of old language next, but it's the better oxidizing agent, and they kind of took that off the AP. The more negative the reduction potential, the more easily an electron's lost, so the more easily oxidized it is, and that's more likely to be happening at the anode. So now if I'm going to draw a voltaic cell, we've already used our reduction potential chart to figure out that Ni would be the cathode and Al would be the anode. Those actual pieces of metal need to be in two separate containers, and this actual piece of Ni is the cathode, the actual solid piece of aluminum is the anode. We would need solutions, and if we looked at our half reactions, we saw that the Ni2 plus was actually needed for this reaction to happen, and that over time the aluminum would turn into Al3 plus, and that would be in this solution. We would need a wire connecting anode to cathode. Electrons would go through the wire from anode to cathode, always, in a salt bridge, so that we can complete the circuit and prevent any charge buildup. We know that reduction's happening here, so I could copy my reduction potential reaction that was right there in the chart right down. You could also see that, if you're being reduced, you should have a decrease in oxidation number. So even if I didn't have that chart and I just had this half cell, I could see that it would be Ni2 plus turning into nickel, so that the oxidation number would be going down and 2 electrons would need to be gained. Notice that it's the Ni2 plus that's actually reduced. The Ni solid is the cathode. So it's two different things. This piece of metal is the cathode, the ion is reduced. And this again should match the actual half reaction on that table, because those were all the reduction half reactions. They should go unchanged. And over time, notice that nickel 2 plus is turning into nickel solid, so that would get kind of plated right onto this cathode, and this would gain mass over time. This is the oxidation half reaction happening here. If it's oxidation, I should be going up in oxidation number. So rather than going, from 3 plus to 0, it should be going from aluminum solid to 3 plus, and then I would need the 3 electrons on the right. So if you compare this to what's on that chart before, notice I actually have to flip the reaction that was on the chart, because I need to show it as oxidation. I need to show it as the electrons being lost. So it's the same half reaction as the chart, but flipped. And so notice it's the same one, but flipped. Over time, aluminum solid will be turning into Al3+, so over time this would be losing mass and decreasing in size. And if I'm talking about the salt bridge, notice electrons are going through the wire this way from anode to cathode, so I would want to send negative charge this way into this oxidation half cell, because over time I have positive charge building up or electrons are leaving, so I want to refill this with negative charge, something that's not involved in the reaction, and over time the Na plus would be coming this way. Now the next question would be, what would be the voltage actually produced by this voltaic cell that I made out of the nickel and aluminum? And I can actually go to that chart to answer the question. So if I come back to that, and again, this is not a separate reference table anymore. What you need would be embedded in the problem. So you probably wouldn't get all of these, just the ones that you would need for the problem. But if I just recircle the ones we were looking at, okay, notice we actually have the potential if these were reduction half reactions. So this one would remain unchanged, and we said this reaction we actually had to flip because it's oxidation that happened, not reduction. So you can do this one of two ways. You could either flip the reaction and then also flip the sign. So instead of negative 1.66, you get positive 1.66 and add them together. Or if you don't want to remember to flip the sign, each time you could just remember you're doing the potential of the cathode half reaction, the reduction half reaction, because that's unchanged, and subtracting from that the reduction potential that's happening at the anode, because this one is actually flipped. So if you think about it, in this case I would be doing negative 0.28, subtracting from it the negative 1.66, which, as I said, is the same thing as if I actually flipped this and added them together instead. Negative 0.28 plus 1.66. Either way, you would get the same answer. Just don't do both. Don't subtract and flip. You either want to flip the sign and add them together, or just always do the cathode one minus the anode one. Your choice. And notice that you're always going to get a positive voltage for a voltaic cell. It always has to be positive. If it's not positive, then you actually picked the wrong anode and cathode, and it's actually going in the opposite direction than you thought. Okay, so just to sum that up, the total cell potential, E of the cell, is actually the sum of the potentials at each electrode. However, since the reduction potentials are listed, you actually have to flip the oxidation one. or, and then add it together. Or you can always do the cathode minus the anode. The reduction potential at the cathode minus the reduction potential at the anode. Either way, you'll get the same answer. Like I said, just don't do both. Remember that the reaction with the more positive reduction potential, that's going to be your reduction half reaction that takes place at the cathode, and the other half reaction would go in reverse so that electrons are lost and it's oxidized, and that half reaction would take place at the anode. E of the cell should always be positive or greater than 0, that means positive, because this is a spontaneous reaction, a redox reaction that happens by itself that produces a flow of electricity. And if you calculate it to be negative, check your work, because either you calculated it wrong, or you picked the wrong anode and cathode and it's actually running in the reverse direction. Okay, and just as a heads up, when a half reaction is reversed, we said we would flip the sign of the reduction potential. However, if you are taking the half reaction and multiplying by an integer, which is what you do when you're balancing by the method of half reactions, the reduction potential remains the same. It's an intensive property, meaning like if you have the density of something and you happen to, take double the amount, the density doesn't double, the density stays the same. So it doesn't matter what you multiply by. So changing the coefficients of a half reaction does not change the reduction potential. So if I was looking at this half reaction, Zn2 plus 2E minus goes to Zn, zinc solid. If I were to multiply everything by 2, the reduction potential does not multiply by 2. It stays exactly the same. So remember, this is something that you might do, multiplying by an integer when you have two half reactions and you're trying to add them together to get the whole thing. It does not change your reduction potential at all. Okay? Take a moment, try this example given this table. Here's the redox reaction happening, the overall redox. Take a moment and figure out the cell potential. So let's check our work. So if you notice here, I have lithium and fluorine, so we're just going to find those in two half reactions. And again, if this were the AP exam, you wouldn't get all of these, just usually the ones that you need. And notice the fluorine's on the left, the lithium solid's on the right. No problem, we'll talk about why in a second. And notice that these are the two reduction potentials that go along with it. So the fluorine is way, way, way more likely to be reduced, which kind of makes sense because fluorine is one of the most reactive nonmetals and it forms negative charges, which is 0 to -1. Oh, that's being reduced. Oh, that makes sense. And lithium's a very reactive, it's group 1 metal. This is more likely to be oxidized. As we see here, it has a much lower reduction potential. So this is going to be my reduction half reaction. We're going to keep it the same way since the electrons are on the left and they're being gained. And we're going to flip this half reaction because it's actually going to be the oxidation half. And that's why the lithium solid, even though it's on the right here, it does end up being on the left there. When if I were to, multiply this by 2 and add these together, I would get then, after I flip that, I would then get this overall reaction. So if I'm getting my reduction, once I have my half reactions of choice, I can either do cathode minus anode, or I could flip this reaction and then add the numbers together. So whichever way I do that, so here if I do, cathode minus the anode one, I get plus 5.92. Or if I were to flip this one, it would be the same thing because I would just do 2.87 plus 3.05 and then get the same answer. And notice it's a positive number. Great. And this would be the combination. This is all the way at the top. This is all the way at the bottom. This is going to be the combination that would give me the highest voltage. So we can also relate this to delta G, if you remember, was Gibbs free energy. And on your formula sheet, you will see there's a bunch of delta G equations, and this one's at the bottom. Delta G equals negative NFE, which is E of the cell. And sometimes you see it without cell. What are these different variables in here? So delta G equals negative. A lot of people forget that negative sign, so don't forget that's there. N is the number of electrons transferred during this redox reaction. So to get that number, it should just be an integer. You got to look at your half reactions. You got to manipulate them so that the electrons are equal. So if one has one electron being gained and the other has 2 lost, you're going to have to multiply the one that has 1 gained by 2, and then your overall number of electrons transferred will be 2. And we'll take a look at how to, in an example. but that is the number of electrons transferred after your half reactions have the same numbers of electrons. F is a constant. It is Faraday's constant. This is also on your formula sheet, kind of in the same section. It says Faraday's constant F, and it tells you coulombs per mole of electrons. So it has units of coulombs per mole. And your cell potential, we just talked about how to find that. Remember, we're doing the cathode minus the anode, or flip the anode and add them together. Since N and F are positive, and we know for a voltaic cell, E of the cell is positive, then notice that there's going to be a negative sign in front. Delta G is going to be negative for a voltaic cell, which makes sense because you have this spontaneous redox reaction that happens by itself without outside intervention. This should be a thermodynamically favorable process. You are taking this chemical energy that happens spontaneously and converting it to electrical energy by making these electrons go through the wire, and you can now actually use this as a battery. You can actually use this equation in an electrolytic cell too. You're just going to end up getting that delta G is positive for an electrolytic cell, which we will talk about another day. Okay, so how does E of the cell relate to delta G? We said if E of the cell is positive, delta G will be negative according to this reaction. It will be thermodynamically favorable or spontaneous, and that's always going to be the case for a voltaic cell. If E of the cell is a negative number, then delta G would be then positive, and the reaction would be thermodynamically unfavorable or non-spontaneous, and it would actually go in the opposite direction. Or it would have to be coupled with something that's spontaneous to force it to happen. This would not be a voltaic cell. If E of the cell is 0, then delta G would also be 0, and the reaction would be at equilibrium, and technically, if this was a battery, that means it would be dead. Okay, let's take a moment. I want you to try this example, and then we will check our work together. Almost done. All right, let's check our work. So notice that here you've got half reactions embedded into the problem, which would be more like the case on an AP exam. Galvanic cell, another name for a voltaic cell. Determine what's oxidized or reduced. Okay, so we have these standard reduction potentials. Remember, the higher it is means the more likely it is to be reduced. So just as a heads up, I put the higher one on top here. The higher one might not be on top, so just check. The AP exam does not have to put them in order for you. But this is the higher one, so this is going to stay the reduction half reaction, and this is what's going to happen at the cathode. And this one would end up being flipped and happen at the anode. So if you're looking at what's oxidized and reduced, the MnO4 minus is the thing that's reduced because the Mn is going from +7 down to +2. And since this is going in reverse, it's the ClO3 minus that is oxidized. The Cl is going from +5 to +7 over here. So you always want to pick the reactants that are oxidized and reduced. And notice they happen to be all ions here. There's actually no solids in here. Okay, write the balanced reaction. So if I want the balanced reaction for the overall, I got to add these two together. If I'm going to add these two together, I got to make sure I've got the same numbers of electrons before I do. This has 5, this has 2, and remember this one's being flipped. So I got to multiply this by 2, multiply this by 5, flip this one, and then add them together. And when I do that, here is my overall reaction. Okay, notice this has 2 MnO4s. This, I get 8 times 2, I get 16 H pluses on this side, but then I have 5 times 2, I've got 10 H pluses on that side, so it reduces, cancels out to have just 6 H plus on the left. And the same thing happens with waters. I've got 8 waters on the right, this becomes flipped, and I get 5 waters on the left, so I end up getting a net of 3 waters on the right. Okay, calculate E of the cell. So even though I'm multiplying these by factors, that has absolutely no influence on E of the cell. I'm just doing cathode minus anode. Or if you like remembering to flip this one instead, it would become negative 1.19 and add them. Your choice, but either way you should get 0.32 volts. It is positive. It should be positive for a voltaic cell as it's spontaneous and it's producing this flow of electrons. Draw and label a voltaic cell, and let's do all of that. Here we go. I need 2 separate containers. These are my reactants for one of them, so they got to go in here, and over time I'm going to get Mn2+, even if I don't start with it. It's not necessarily needed to start, but it will be produced over time. And in this one, I need the ClO3 minus in there to start with, and over time, these two things would end up being produced since we flipped that half reaction. Okay, since neither of them have a metal in it, let's use platinum or maybe something like graphite, something that's unreactive but still conducts electricity. This piece of platinum would be my anode since this is my oxidation half, and this is my reduction half cell, so this would be the cathode. There's going to be no change in mass of these over time because I've got ions turning into ions. There's no solids being lost or gained. So over time, the mass of these would not change. So if you remember in the last video, I asked, hey, what happens with mass over time? And a lot of times the anode decreased, the cathode increased. That's not always true. You've got to look at your half reactions and see what's going on. Okay, we need a wire to connect anode to cathode. Electrons go through the wire from anode to cathode. If you flip what's on each side, you'll have electrons going the other way. Salt bridge. If electrons or negative charges going to the left, negative ions would go through the right through the salt bridge. Because you're having negative leave this side, you got to add more negative in this side. You're having a buildup of negative on that side, but you got to add the positive charge this way. Salt bridge should have something not involved in the reaction, so no perchlorate, no chlorate, no Mn2+, something not involved. Okay, and we already have our oxidation and reduction half reactions up there. Just remember this one's flipped. All right, and then it says, ignore that, let's do calculate delta G. So if we go back to that equation, delta G is negative N, which is the number of electrons. Oh, let's see, there's 5 times 2. Remember, we multiply by a number to get the electrons equal. There's 10 electrons. And those electrons didn't appear in the overall reaction. We got to kind of go back to our half reactions to look at it. So 10 electrons. And I'm going to show you how units kind of cancel out here. F was Faraday's constant. It's on our formula sheet. We can copy that. It's coulombs per mole of electrons. Oh, notice moles of electrons are going to cancel. And E of the cell was our voltage that we got by doing cathode minus anode. And volts, if you remember, I had showed from the formula sheet that volts was the same as joules per coulomb. So it might be helpful to write it as the unit joules per coulomb because you'll see that's how coulombs cancel out. And that's how you get a unit of joules, a unit of energy for Gibbs free energy. Okay, so again, this is the total number of electrons. The electrons you canceled out when, balancing your half reactions, getting them equal in electrons, Faraday's constant, and our E of the cell. And don't forget this negative sign. A lot of people forget to carry it down. Overall, your delta G should be negative for a voltaic cell because it is a spontaneous or thermodynamically favorable reaction that's happening. And a lot of the times for delta G, they might ask for kilojoules instead. Whenever you're plugging in here, notice you're going to be getting you're going to be getting joules, so please pay attention to units. It might be helpful to plug in with units. I always suggest plugging in with units, and if you are asked for kilojoules instead, which a lot of times delta G is written in kilojoules, then don't forget to divide by 1,000. And again, notice this is negative because a galvanic or a voltaic cell is spontaneous and thermodynamically favorable. And a heads up about this equation, this delta G equation, if you can calculate E of the cell, notice that these are all equal to delta G. So these are all equal to each other. I could set any of these equations equal to each other. So if I have E of the cell, the potential of the cell, I actually could also calculate K for the reaction, the equilibrium constant. Or vice versa, if I have the equilibrium constant, I could set these two equations equal to each other and I can calculate E of the cell. So a heads up about that, you could see a problem with that. And just beware that both of these have negative signs. So you're going to end up noticing that if E of the cell is a positive number, meaning that, it's thermodynamically favorable, you're going to get a K that's larger than 1, which makes sense. It favors the products. It favors going forward. It is thermodynamically favorable.